Hey, Calc students, this is Mr. Beck. Today we're going to be talking about Slipfield's and Euler's method. Now, Slipfield's and Euler's method is something that involve differential equations, which begs the question, what is a differential equation? Differential equation is an equation that involves x, y, and derivatives of y. It's called a first order differential equation if it involves the first derivative. It's called a second order differential equation if it involves the second derivative, et cetera, et cetera. So a lot of the times of what we've done in the past where we've said dy dx equals, say, x squared, and then we have y equals 1/3 x cubed. So you know me, I haven't really been a fan in the past of using the y prime notation just because y prime should be reserved for differential equations. So if y prime equals x squared, same thing is true, y is 1/3 x cubed. Now, the difference is that y prime is used in context with other components to an actual relationship that we measure in real life. And that's why differential equations are very, very important, because many times derivatives and functions and how things change, they're all kind of wrapped together into one big equation that works together. That's what math's all about. It's about modeling the real world. So sometimes modeling the real world, it's not just about using like an independent variable and a dependent variable, but the rates of change get thrown in there too, which is what the differential equation is. Now, I have this boxed here. That's because a lot of the times the AP will say y equals f of x. So they're showing that they want you to actually come up with this function as a result. And we'll see that more next time in our notes when we're talking about solving differential equations. We're going to solve some pretty basic ones here, but today our focus is going to be more Slipfield and then Euler's method that goes along with it. So a solution to the differential equation. We have a solution to the differential equation if the equation is satisfied when y and the derivatives are replaced by our function and its derivatives. We can see that with our first example here. So we have our function y equals e to the negative 2x. To prove that it's a solution, we are going to go ahead and find the derivative. So y prime is negative 2 e to the negative 2x. And then we plug y prime in, then we plug y in. And is it true? Does that equal 0? Yes, it does. 0 equals 0. And QED. Proved as directed. This one's a little bit more complicated. So we have our function x squared e to the x minus 5x squared. So when we come up with y prime, we do have a product rule. So we have u dv plus v du. So x squared e to the x plus 2x e to the x and then minus 10x. So we plug that in right here for y prime, multiplied by x. And you can see that I've already done some of the algebra here. Minus 2 times y. And if we distribute, we get x cubed e to the x. We get 2x squared e to the x. And we have minus 10x squared. Then negative 2x squared e to the x plus 10x squared. We can see that some of those things cancel. And really what we're left with is just what's remaining. So yes, we verified, yes, this is a solution to the differential equation. So verifying that their solution is pretty easy. We just plug in the y, we plug in the derivatives. Now, when we're actually solving differential equations, it's really just using integration techniques. So we already did a little bit of this. We're going to go into it a little bit more. So if s double prime equals negative 32, then s prime, if we take the integral of both sides, negative 32t plus, usually I put c1, but really, since this is position of velocity and acceleration, we can call it initial velocity. And then integrate one more time, s of t is negative 16t squared plus initial velocity times t plus initial position. So it's kind of like a proof of why, or that basic relationship between position, acceleration, position, velocity, and acceleration. So then if we have additional information, we could find the particular solution to the family of curves. What do I mean by that is that if we have a differential equation, not just differential equation, but if we have a function that we're working with and we take the integral, we always have that plus c. That plus c says it could be, it could be anything. So it's a family of curves when we take the integral. When we were working with differential equations, the same thing's true. we can have a whole family of curves that are going to be true. But then if we have some specific information, we can say exactly which one is true. And then slope fields will help us visualize that as well. And I'll show you what I mean, what's going on in my head. So first things first, if we have our s double prime is negative 32, if we said s prime of 1 is 32, then I'm going to take this information right here. My initial velocity, I could solve for it. So 32 is negative 32 times 1 plus initial velocity. So my initial velocity is 64. Plug that in. Then integrate one more time. Integrate one more time. We have negative 64 plus 128 plus initial position is 96. So we get our initial position is 32. What I was using is that we know that our position at time 2 is 96. Put that into our information, and we get the particular solution. Now, I would say the particular solution, or the particular curve in this case, is going to be the one that satisfies all the information from our differential equations. So what I was talking about with slope fields, they're a way for us to visualize what the actual solution is. Let me go ahead and switch screens on you quickly. So a slope field is a way for us to visualize what curve is actually going to fit that situation. So what you can see here is you're seeing kind of like a ghosting image of what, based off of our differential equation, which I have right here, what would the curve look like based off of initial condition. So we know that when we integrate, we have a family of curves that result. This slope field visualizes that whole family of curves. And the moment we lock in to say this is our initial condition, it locks into a specific member of that family of curves. So I do like this because it kind of helps us visualize exactly what's going on. We could change our differential equation. Let's say 2 plus y, see what happens. Looks like so. If you notice, this looks something like an exponential function. There's a reason for that. We'll talk about that as well. So this can be a number of curves. Now, what's going on here is once we have locked in or a locked in point, then the rest of the curve will follow along the actual slopes. So what these bars represent are the slopes at those individual points. What I like about this one is we can make more and more and more, so we can have a little bit more accuracy in terms of what that curve would look like if we were to draw it, which we're going to. But again, this point kind of locks in where exactly where will the object flow. I guess what I'm thinking in my mind is this is almost like a wind current, and you can see these are this almost looks like a wind current in general, but wind current is if we have a point that's locked in, the rest of the curve will flow along that current of the slopes. And I don't know if that's the best analogy, but it's kind of the way that I think about it. But anyway, they help us visualize what that family of solutions are going to look like. Some can be solved, some differential equations can be solved algebraically, which is what we are going to be doing. We've already done, but we're going to do some more work with that. Some actually can't, though. In fact, if I have y prime equals e to the x squared, this is not something, so this is not integrable. This is not integrable. Sometimes we could use slope fields to help us visualize what that curve is actually going to look like. So anyway, if we have a known function, then we can interpret dy dx as a slope to the tangent line at any point. What we're going to be doing is we're going to be taking a rectangular grid of points. With that rectangular grid of points, we're going to calculate the slopes at all these random places, and then we will draw line segments to create this actual slope field. So I have a couple already drawn in here, and then we're going to draw some in specifically. So this one, this is our slope field for dy dx equals 2x. Now, if we go ahead and solve this differential equation, which we're not going to be doing a whole lot of that just yet, but To solve this, we use what's called a separation of variables method. So y is x squared plus c. So that x squared plus c, if we draw in some specific solutions, so you see 2 drawn in there already. Let me go ahead and say what happens if I have the point here. There's a slope 0, and we have a slope. I'm sort of following along with all the slopes that are there. And I'm creating the curve as a result. So I'm following along with the slopes. I'm following along with that wind path is what I was talking about before. This one I have here, dy dx is x squared. So if dy dx is x squared, one of the ways that I tend to look at it also is if I know that my derivative is x squared, that I know that the actual function itself is a cubic. The function itself is a cubic. You can see that this is sort of following along with a cubic model. And that's what I have over here. So if I have a specific point, I can follow along with that cubic model. It's a little too steep there. Looking something like that. So if we have to draw in functions or draw in the curve based off of a given point, it's not always easy to do, which is why we tend to like to use technology to do that. But anyway, it's not a perfect science, but it helps us estimate. You'll find the calculus is all about estimation. Now, if we go to actually draw on a slope field, to draw on a slope field, there are a couple different ways that you can approach this. Change colors. One of the things that we can do, this is kind of like the very, very tedious way, is we could just choose a series of points and say, okay, if I want the point 0, 0, then I know that my slope field is going to be the x coordinate plus 1, so 0 plus 1 is 1. So at the point 1, 1, the slope is going to be 1 plus 1, which is 2. So this should have a slope of 2. The first point has a slope of 1. We could choose a random point, 2, 5. 2, 5 is not on here. How about 2, 1? So 2, 1, the slope is going to be 2 plus 1, which is 3. So 2, 1, this should be a slope of 3. And that's what this slope field represents. It's kind of a short bar that represents what the actual slope is at that point. So the approach that I took so far has been a very, very tedious one. That tedious slope, that tedious way of doing things, it's not perfect, but there are faster ways. And in fact, one of those faster ways is to say, okay, let's see if we could generalize based off the situation. So slope field is going to say for no matter what, we're going to take our x value and add 1. So we can start choosing what are some x values that we have. If whenever x is 0, we're always going to have a slope of 0 plus 1. Whenever x is 1, we're always going to have a slope of 1 plus 1, which is 2. So we could start generalizing. We could fill in things a little bit more efficiently. Another way that we can look at it is to say, okay, what happens if I want to know what my specific slope is? In fact, having a slope of 0 is going to be something that's very, very important. So if we ever want to know, like, what is our actual slope, we can put that in. Our slope of 0 is x plus 1 and solve. So whenever x equals -1, we're always going to have a slope of 0, which we actually do. If I wanted to say the specific slope of when is my slope going to be -3, my slope's going to be -3 whenever x plus 1 is -3. So when x is -4, we're going to have a slope of -3, which is not on here. But anyway, generalize and start seeing different patterns. And the more patterns you can see, the faster you're going to be able to draw our slope field. For this one right here, let me kind of take that approach to the problem. When is my slope going to actually equal 0? My slope is going to equal 0 whenever y equals 1. So if you see, that's why that my slopes along the whole line y equals 1 are going to be 0. Now this slope field is going to be dependent upon my y value. So where are my slopes? -1. My slopes are -1. And remember, this is my slope. My slope is -1 at y equals 1, or at y minus 1. So y is going to be 0 whenever my slope is going to be 1. So I could draw on my slopes of 1 throughout, or sorry, -1. And I can continue that pattern over and over again. What about this one? And you can see this is the one that I visualized with you already. So dy dx is x plus y. We could see here, we saw like a different result. But anyway, this is what I did here is, where is my slope going to be 2? My slope is going to be 2 whenever x plus y equals 2. So if I solve for y, along the line y equals negative x plus 2, I have a slope of 2. This is what I have here. I can continue that and say, when is my slope 1? Whenever x plus y equals 1, which would be along that line. My slope is 0, and you see I have that right here. My slope is 0 along the line y equals negative x, and that is because 0 is x plus y. So whenever y equals negative x, I'm going to have a slope of 0. So again, this is going to be a way that we can make life a little bit easier in terms of drawing our slopes. We can, again, find the pattern. What happens if you can't find the pattern that easily? You're just going to have to start plugging in some x's and y's, and we'll go through the slow, tedious approach. Now, slow and tedious doesn't mean it's necessarily bad, it's just slow and tedious. For this one, draw a slope field for when dy dx is negative y over x. As I mentioned before, one of the ways that we can do this is by finding patterns. Whenever x is 0, I'm going to have some undefined slopes. Whenever y is 0, I'm going to have slopes of 0. Whenever x and y are the same, I'm always going to have a slope of negative 1, which is what's going along here. Whenever x and y have the same value but are opposite signs, I'm going to have a slope of 1. This is what's going along here. And then really to find all the other points, I did it by plugging in just x and y values. One of the things that I do want to show you is if I have undefined slopes do have a vertical bar. The AP will never ask you to draw the undefined slopes, but for me, those are kind of important too, because undefined slopes are a line that are straight up and down. So undefined slopes are a slope of 0 for the inverse function. And so what happens if our function is based off of y and not of x? Then that undefined slope is going to be kind of important for us to see. So if you notice here, I have kind of like an open. I really probably shouldn't draw anything there. But whenever you have 0 over 0, 0 over 0 is truly undefined. And so we don't know any actual slope there. Something else, and this is kind of like a little matching activity. How do we go ahead and go through and match these different situations? This is where we can look at patterns. So go back. So whenever my x value is 0, I have a slope of 0. Whenever my y value is 0, I have undefined slopes. And if you see, that kind of matches along the situation I have A there. This kind of looks like a quadratic almost right here. So which one of these would end up being a quadratic? That would be this one right here. You notice I'm kind of going through different ways of approaching this. What I could also say is when my x value is -2, I have a slope of 0. Oh, that would be right here. For C, I have a slope of 0. So I have a slope of 0 along the line y equals x. So my slope is 0 along y equals x. That's going to be right here. So probably should have finished that one, y minus x equals 0. And then the last one, just to generalize, whenever y is 0, I have a slope of 0. Whatever the y value is, I have the slope of y, which is this one right here. All right, some continuing matching. Basically, what we could do is we could use the function itself to say what, or we could use the slope field to say what function does that look like. For instance, This looks like the sine graph. Since that looks like the sine graph, that would be E right here. This one right here is our cosine graph. This is going to be our constant function. So with our constant function, that would be right there. I know I'm kind of jumping around. I'm just trying to find something that actually has patterns that we can see. So this is our cubic function. So that cubic function would be right there. Linear. Trying to, are there any other easier ones? So this kind of looks like it's going to be almost, yeah, that's our quadratic one. So if you notice, I'm just trying to match up things that sort of make sense. Anyway, then we have Euler's method. Euler's method is our way to actually model our function. We're going to model our function through tangent lines. So tangent lines, we have our y value plus our rate of change times how much it changes. So we have our known plus change times the amount of change. So tangent line approximations. So what we could do is we can draw in our actual curves that way. So when we draw in our curves, it's going to be a poor model, a poor representation of what's going on, but it's at least an approximation that has some merit to it. So again, that's whenever we have a situation like, what does e to the x squared look like? E to the x squared is not something that we can integrate, so we can't find the actual curve, but we could use Euler's method to actually come up with what that curve would look like. So we're going to take our initial point, y of 0 equals 4. So if we have 0, 4, and I tend to do this in a table. So we take whatever the y value is, take the rate of change times how much has changed. So my goal is to approximate y of 1 using Euler's method. And I'm going to go in steps of 0.2. So whenever x is 0.2, then I'm going to follow my differential equation. My differential equation will take the y value minus 2. This can be the previous y value. So the y value from before, take that y value minus 2 times the amount of change, and I get my new value of 4.4. Then 4.4 plus 4.4 minus 2 times 0.2, get my new y value, plug that in, and et cetera, I can keep going over and over again. Now, what I did on the right side, and I kind of alluded to this already, I said, hey, it looks like an exponential function. One of the things that we're going to learn next time is if we ever have a differential equation that's based off of y, then it's a direct variation and turns into an exponential model. If you see here, I separated my variables. When I separated my variables, integrate both sides. After integrating both sides, I can solve it for the function y. And then I could use my initial condition. This is kind of a preview for what we're going to be doing next time. Use my initial condition to say the actual function that's going to be modeled here is 2e to the x plus 2. And if you notice, that is the actual y value. This is the approximation if I continue with Euler's method. So are they the same? No. In fact, in my opinion, they're kind of far off. But if you look at the tangent line approximations, we're going to be doing the tangent line approximation off of, I guess, a better way of saying that, we're going to be using our tangent line approximations to fit this curve. So we're going to get, as I said, a poor representation, but it's at least a function model that is viable. Another problem, again, if I'm starting off with y of 0 equals 3, my goal is to find y of 0.5. So my steps are of 0.1. So I start off with my initial point, take my y value, my differential equation times the amount of change, and I get my new y value. That y value, plug it into the differential equation times the amount of change, get my new y value, a new y value, plug it into my differential equation times the amount of change, get the new y value, et cetera, until I get to the y value of what I want. So I will hopefully find a good visual representation or something to show you a little bit more about Euler's method. I'll be looking for those kind of details. But anyway, until later, bye.